Alright, this is a very important chapter for those of you interested in the health sciences and agriculture, because all living organisms, ignoring all metaphysical aspects, are simply breathing, moving solutions. Therefore, if you want to understand biochemistry, you have to understand solution chemistry. Solutions are a special type of homogeneous mixtures in which two substances are mixed on a molecular level or a molecular ionic level. They consist of two parts, a solvent and a solute. We refer to the part of a solution that is present in the lesser amount as the solute. We refer to the substance that is present in the greater amount as the solvent. One of the defining characteristics of a solution is that you cannot separate a solution by filtration. If you can remove something from a liquid by filtering it, you do not have a solution. Solutions cannot be separated by filtration. They can, however, be separated by evaporation. Now, one of the things that we talked about way back in the first chapter, I believe, was the nature of solutions. Remember that solutions are mathematically uniform homogeneous mixtures. Every single part of a solution is mathematically the same as any other part. Why is that? Because your solutes spread evenly throughout the solution. It's also important to note that while you can't see individual particles of solute, you can see them giving color to a solution. One thing you should realize is that if you can see particles floating in a liquid, you don't have a solution. You have probably a suspension or what's known as a colloid mixture, which is basically a solution with really big particles. But if you can see the solute particles, you don't have a solution. Up till now, I've talked about solutions being a liquid solvent with something dissolved in it. However, you don't always have to have a liquid solvent. You can have a gas-gas solution, for example, the air that we breathe in. You can have a gas in a liquid, for example, soda or pine sol. You can also have liquids in liquids, vinegar, for example. Salt water would be an example of a solid in a liquid. You can also have solid in solid solutions, and those are referred to as alloys. The most common alloy that you're used to hearing about is brass. It turns out that steel is also a solution of carbon dissolved in iron. So solutions can be more than just liquid-liquid. They can also be gas-liquid, liquid-liquid, solid-liquid, etc. Water is perhaps the most common solvent. We've already spent time talking about the nature of water as a solvent. Water is a highly polar molecule that is capable of forming hydrogen bonds. Remember, water is such a polar molecule that it can actually pull apart ions in an ionic compound. Remember, this should be review for you. We talked about this when we looked at precipitation reactions and ionic equations. Remember that positive ions are going to be attracted to the partial negative charge on oxygen, and negative ions are going to be attracted to the partial positive charge on hydrogen atoms of water. We've previously talked about intermolecular forces. Intermolecular forces are key to understanding why things dissolve in each other. You've probably heard the term like dissolves like. When two substances form a solution, they're intermingling or mixing with each other. They have to have a way of interacting if they're going to mix with each other. They interact with each other by having a common attraction, or a common intermolecular force. What that means is that polar substances dissolve other polar substances. Nonpolar substances dissolve nonpolar substances. Ionic substances dissolve in polar substances. Why? Because those polar substances have those partial negative, partial positive charges that can interact with the positive and negative charge on the ions in ionic compounds. So when you hear the expression that oil and water don't mix, you know that is true because oil's nonpolar, water's polar, and there's no common intermolecular force for them to interact with. This slide illustrates what happens when you dissolve methanol in water. Notice that the molecules of methanol are interacting with each other. Those little pale blue lines you see are hydrogen bonds. Hydrogen bonding between the molecules of methanol. And then if you look at the slide that shows water, you see that water molecules are also hydrogen bonded to each other by those thin blue lines. Well, when you mix the two, they're capable of interacting or forming hydrogen bonds with each other. In other words, they're able to relate and intermix due to a common intermolecular force. Alright, let's talk about solubility. Specifically, let's put mathematical context to solubility. Let's start by defining what solubility is. Solubility is the maximum amount of solute that dissolves in a specific amount of solvent. You express solubility as grams of solute in 100 grams of solvent. Usually that solvent is water. In addition to mathematically describing solubility, using that formula you saw on the last slide, we also use relative terms to describe solubility. Two of those relative terms are saturated solutions and unsaturated solutions. A saturated solution contains the maximum amount of solute that can dissolve at a given temperature. A key way to tell that you have a saturated solution is if you keep adding solute, you see it begin to appear at the bottom of the container or floating on top of your container. In other words, it's not dissolving. So you have a saturated solution when you can't dissolve any more solute into your solution. An unsaturated solution contains less than the maximum amount of solute. You can dissolve more solute into an unsaturated solution. You can't into a saturated solution. A way to tell whether or not your solution is unsaturated or saturated is if you have an unsaturated solution and you add more solute, it will disappear. It won't settle to the bottom and it won't float on top. It'll dissolve into the solution. Remember, to answer all these questions, what you want to do is you want to set up a ratio of grams of solute to 100 grams of water. So you may have to double or half or multiply by 4, divide by 4 your concentrations in order to achieve that ratio. Remember, when I gave my definition of a saturated solution, I said it's the maximum amount of solute that can dissolve in a solution at a given temperature. Solubility depends on temperature. For most solids, as temperature increases, so does solubility. For most gases, it's the exact opposite. As you increase temperature, the solubility of a gas decreases. Easy way to remember this is if you make Jell-O, you heat your Jell-O and dump in your packet, right? So that you can dissolve more. There's also other reasons for that, but that's one of the reasons you heat water before you make your Jell-O. Another thing to think about is what happens when your soda cans get really hot. They bulge out, right? Leave a soda can in your car on a hot day, and you'll see that bottom bulge out and that top bulge out because your carbon dioxide is less soluble in that can under hot conditions. The solubility of a gas is also related to the vapor pressure of the gas directly above the liquid. The higher the pressure of a gas above a liquid, the more of that will dissolve, and the more of the gas that will dissolve in the liquid. Again, let's talk about soda, just like we did in the last slide. Your soda cans are always pressurized, right? If you drop one and it hits, it explodes because it's under pressure. The reason it's under pressure is they pump that thing full of carbon dioxide gas. If you looked inside your soda can, you notice that the top of your soda can doesn't contain any soda in it. What it actually contains is a fine layer of carbon dioxide. By having a very high pressure of carbon dioxide, you can force more carbon dioxide to dissolve in your soda. When you open your soda can, what's happening? You're letting all that carbon dioxide out. So instead of having pure carbon dioxide over the surface of your soda at a high pressure, you now have a mixture of gases, and you have less carbon dioxide right above your solution, which means that less carbon dioxide is going to dissolve in your solution, and we're going to see carbon dioxide leave our soda in the form of bubbles. You can also see this when you look at your 2 liters. What happens when you open a 2 liter? You get that hiss. Carbon dioxide escapes. You pour out your soda, you retighten it. After you retighten it, you don't have any carbon dioxide in that 2 liter. You just have air, which means that, well, which contains some carbon dioxide, but you don't have a lot of carbon dioxide. So the solubility of that carbon dioxide in your soda in your 2 liters is less. So carbon dioxide is going to leave there and leave your soda and build up in that top of your 2 liter. So that next time you open that 2 liter again, what happens? It hisses again, because we've once again maintained an equilibrium. We've seen that carbon dioxide leave to equalize the pressure. Bottom line, Henry's law states that the solubility of a gas is directly proportional to the vapor pressure of the gas above the liquid.